Hello and welcome to the session on the mechatronic. The topic for the today is the analysis of the mechatronic system part 2. Part 1 we have already built that particular video. So I am Professor Khond working with the KKWA College of Engineering, Nasik. So let us set a learning objectives for this particular session. So in the learning objective we will be focusing on the second order system analysis, then transient response specification, then frequency response specification, and the stability using the Bode plots. So let us start the session. So that is the system analysis. Let us say in the system analysis, so we'll be having the two kinds of analysis over here. One is the time response analysis, another one is the frequency response analysis. So in the time response analysis, so as you can see that system A, so it is being input from the different things. One may be the step input, another may be the ramp input, another one may be the parabolic input. So let us say this may be the different kinds of input and there is the output, so we can analyze the output. Okay, so in the frequency response input, so there are different frequencies: first frequency, second frequency, third frequency. Let us say different frequencies are the input to the system and we are analyzing the output. So that is the difference between time response and the frequency response. So here we are taking, in the time response we are taking the different standard inputs. It may be step, it may be ramp, it may be parabola. But in the frequency response analysis we are taking the different, the input is being varied with the frequency. Okay, now we are concentrating on the second order system. So the control system consisting of number of system, let's say zero order system, first order system, and the second order system. So zero order, it is being characterized by one variable. So if you differentiate that particular variable, it will become the first order system. Now again, if you differentiate that first order system, it will become the second order system. So let us say x is the displacement. So if you differentiate it, it will become velocity, that is equal to dx by dt. Again, if you differentiate it, that will become the d square x by dt square. So that will become the acceleration. So that is the second d square x by dt square, that will become the acceleration, and that becomes our second order system normally. So when you are talking about the control system, so control system is being defined by using the differential equation. So whenever you say differential equation, normally it is second order differential equation. Okay, so that's why our main focus is on the second order system. Now in the second order system, so second order system transfer function, we are talking about normally transfer function. So whenever you say the control system, we talk about the transfer function, that is the Laplace transform of output upon Laplace transform of input. Okay, so that is equal to C of S, that is the controlled output, upon the reference input, which is equal to omega n square upon n square plus twice zeta omega n s plus omega n square, where zeta represents the damping ratio and omega represents the natural frequency of the system. Okay, so it is, so second order system, it is being characterized by this particular equation. Now if you say a characteristic polynomial of a second order system, so that being the denominator, so s square plus twice zeta omega ns plus omega n square. So if you take the roots, so roots will become s minus s1 and s minus s2, that will be equal to 0. So closed loop poles for the system are s1 and s2, so it should be s2 over here. So that means, so by taking the by calculating the roots of the equation, that is minus beta plus minus under root b4 b square minus 4ac. So by using that condition, we can get the roots over here. So you will be getting the roots as first one is positive root, another is the negative root. Okay, so s1 will be equal to minus omega n zeta plus omega n under root zeta square minus 1, and another root is minus root, negative root. First one is positive root, another one is the negative root. Okay, so in this case, so this is, we can say it is being called as poles of the system. Now in this case, we have taken the damping ratio zeta. So damping means every system has a tendency to oppose the oscillatory behavior of the system, which is known as damping. Now in this case, we are having the damping factor, or we can say it is damping ratio. The damping in any system is measured by the factor or ratio which is known as damping ratio zeta. So that means it is damping coefficient upon critical damping coefficient. So that particular ratio is being called as damping. Now these are the terms which are normally used in the kind of so you can say in the second order system, or we can say in the vibration kind of thing. So this can be useful. So these are the terms which are normally used in vibration kind of system. So system becomes unstable. Okay, so the system may be stable. So normally balancing, vibration, so these are the terms which is normally used in balancing and vibration. Okay. Now analysis of the second order system for the step input. So let us say step input being given and the second order system will be given. So for the say step input, the poles are, so then normally four conditions are there. If the roots are real and unequal, if the poles are real and unequal, that may be zeta square minus 1 greater than 0, is equal to 0, less than 0, and is equal to 0. Equal to 0 means there is no damping. So whenever there is no damping, the system vibrates like this, or the system oscillates like this. So whenever is greater than 0, it is getting greater than 0, the system become over damped. Whenever it is equal to 0, that becomes the system is critically damped, and it is being shown like this. Whenever it is less than 1, the system is under damped. Under damped systems normally preferable, okay, instead of over damped, the under damped systems are normally preferable. Okay, so the poles location will be like this. Here the roots are real and unequal, equal, then complex. So here we are having the this is what sigma being the real part, j omega being the imaginary part, and this is the s plane. Okay, so whenever you are talking about the s plane, real part and the imaginary part. Okay, so in the imaginary part, these are the real roots, but these are unequal, one positive, one negative. Okay, so one will be like this, one will be over here. So this is plus and here it is minus, but both the roots are real. Okay, so here in this case, all the roots, two roots lies on the same point. So we'll be having the roots, two roots, s1 s2, it will lie in this part, because it is equal to 0. So only thing remaining is this particular part. In the less than 1, so it consists of the imaginary part, because less than 1 means this particular less than 0, that means under root. So it is less than 1, that means the j part, that is imaginary part, comes into picture. So that's why there is imaginary one, imaginary two roots. So real part and imaginary part, both part will be there in the roots. Okay, so this is the part. Okay, so whenever you can say the analysis for the second order system for the step input, it consists of four parts. So it may be the system may be under damped, the system may be over damped, system may be critical damped, or the system may be undamped. The controller, the main name of the controller is to reduce this fluctuation. So that is what the study is going to be there, and to reduce the fluctuation and to reduce the error band. Okay, so in this case, in the transient response, so there are certain times: delay time, rise time, peak overshoot, setting time. So first one is the delay time. So 0 to 50. So whenever the system gives 50% output, that we call as delay time. Second one is the rise time. So whenever the system gives 10% of the output and the 90% of the output, so whenever the system output ranges between 10 to 50%, it being called as rise time. Okay, then peak time. So first peak, whatever the time it will get, so that being called as peak time. Then peak overshoot, so magnitude above the 100%, so that is being called as peak overshoot. Okay, then the next one is the setting time. So how much time it will take to settle, so that is being called as settling time. So consider 2% of tolerance band, that means the error band being taken, 2% of the error band. So 100, so this is the desired output, so 2% over here, 2% over here. So within this two range, my output should lie. So that has been taken as the tolerance band. Okay, now whatever the things being written over here, so these are the formulae. So for delay time it is being calculated 1 plus 0.7 zeta upon omega n, that is the natural frequency. Rise time pi minus theta, that is the angle, upon omega d. Omega d is the damped natural frequency. So damped natural frequency is equal to omega n square under root 1 minus zeta square. Similarly, peak time will be equal to pi by omega d. Similarly, percentage mp will be equal to e to the power minus zeta pi upon under root 1 minus zeta square into 100%. Okay. Then for the setting time it is equal to ts will be equal to 4 upon zeta omega n. So only three factors we are considering. First one is the natural frequency, second one is the damping factor, and the third one considered in the form of damped natural frequency. Then coming to the frequency response analysis, so let us say a system is having certain transfer function, okay, or we can say a system. Okay, the system is having the input, so system is having the input in the frequency form. Okay, the a represent the a sin omega t. So whenever it says a sin omega t, the system is having the signal is having a sin omega t as the input. The output may be in this particular form. So b is the amplitude and phi is the phase change. So there may be a phase change, so it may be like this. So initial it may be like this, and afterwards, after the system perform, so it will be like this. So your input, so this is, let us say this is the input a sin omega t, and this is the output, wherein a being the amplitude, here is the b is the output amplitude, a is the input amplitude, and omega t plus phi. So phi being the phase angle, so it is out of phase with the input. So this particular kind of thing, so that is being the phase. So for the frequency response, the different frequencies are being the input. Okay, so whenever you say frequency domain specification for the second order system, so there are four parameters. So first one is the resonance frequency. So it is the frequency at which magnitude of the frequency response has peak value for the first time. So it is denoted by omega r, which is given as omega n under root 1 minus twice zeta square. Another kind of thing is resonant peak. It is the peak maximum value of the magnitude of m j omega. It is denoted by mr, so which is equal to 1 upon twice zeta under root 1 minus zeta square. M of j omega. So normally in the Laplace form we are taken m of s, m being the magnitude, m of s. So s being replaced by sigma plus j omega. So real part we are not considering, sigma part we are not considering, only the imaginary part has been considered here. Okay, so that is what we are concentrating on, we are focusing on. So now the third one is the bandwidth. It is the range of the frequencies over which the magnitude m j omega drops to 70.7% from the zero frequency value. Okay, also it is the range of the frequency between 0 dB level, that is decibel level, and minus 3 decibel level of magnitude m j omega is called bandwidth. So this is the formula for the bandwidth. Omega b is equal to omega n under root 1 minus twice of zeta square plus under root twice minus 4 zeta square plus 4 zeta to the power 4. So this is the formula for the bandwidth. Now another specification is cutoff rate. So that is the slope of the magnitude of the frequency response function at higher frequency, that is above resonant frequency. It also gives the ability to distinguish the signals from the noise. So it is the slope of the magnitude of the frequency response function. Let us say, so whatever the frequency domain specifications are being given, so these are being shown over here. So in the form of gain, in the form of phase. So these are the particulars. mr, that is the resonant magnitude, resonant thing. Here omega r, that is the resonant frequency. Omega c, that is the bandwidth. Then resonant peak. So this is the resonant peak, resonant frequency, bandwidth. Okay, so 0.707. Okay, So whenever we are talking about the cutoff rate, so cutoff rate is this particular line, so tangent to the curve, this particular curve, so that is big and extending up to the frequency, so that being the cutoff line. Okay, so when you are seeing the normally in the frequency domain specifications, we are taking m, that is the magnitude, and the phase angle is phi. So phase angle varies from 0 to omega in the reverse direction, so that is the minus phase, that is the fourth quadrant is being there. Okay, while the magnitude varies with respect to frequency, omega being the frequency, these are the frequency value and these are the amplitude value. Okay, so this is the part, we can say it is the part of gain, it is the part of phase. Okay, now we are having the one numerical upon this. So let us say a unity feedback system has gain of 16 upon s into s plus 5. So if the step input is given, calculate the damping ratio, overshoot, and the setting time. Let us say g of s and h of s is equal to 1 because it is a unity feedback system. Okay, so you have to determine the closed loop transfer function. So formula is c of s upon r of s is equal to g upon 1 plus g into h. Normally plus, that means it is a negative feedback. Okay, if it is minus, that means it is a positive feedback. Okay, here it is plus, that means it is a negative feedback. Okay, so put the values of g and h. After putting the value, so it is being simplified as 16 upon s square plus 5s plus 16. Okay, then the next thing is settling time. Settling time is having the formula upon is equal to 4 upon zeta omega n, so it is equal to 1.6 seconds. Similarly, we are supposed to calculate the overshoot, percentage overshoot. The formula is this one, so values will be zeta omega pi upon under root 1 minus zeta square. So putting the values, we will be getting the percentage overshoot as 8.08%. A very simple kind of numerical. Then the next thing is we are focusing on the Bode plots. So we are supposed to get the stability analysis using the Bode plot. First we will see what are Bode plots. Okay, first we will see what are Bode plots. So Bode plot or the Bode diagram consists of two plots. First one is the magnitude plot, another one is the phase plot. So these are the magnitude plot and this is what we can say it is a phase plot. So magnitude means a kind of gain, phase means the phase angle. So x-axis represents the angular frequency, in both the plots. Okay, but it is on the logarithmic scale. So we are plotting the Bode plot on the log paper. Okay, y-axis represents the magnitude, that is linear scale of the transfer function in the magnitude plot, and the phase angle of the open loop transfer function in the phase plot. Okay, so we'll be having g of h, j omega in decibel. Okay, and here phi of omega, that is in the phase. Okay, so 0, then minus 180, and below that. So it will vary like this normally, and it is being vary like this. So positive region and the negative region. So normally the magnitude of open loop transfer function in decibel is m, that is magnitude will be equal to 20 log of g of j omega, h of j omega. So normally g of s, h of s, that is the open loop transfer function. So s being replaced by j omega. Normally s is equal to sigma plus j omega, but we are not considering the real part sigma, we are only considering the imaginary part. Okay, now the next thing is phase angle of the open loop transfer function in degrees, that is equal to phi, which is equal to angle of g of s and h of s. So replace s by j omega, so angle of g of j omega, h of j omega. Now the note here that the base of the logarithm is 10. Okay, now these are the Bode plots, representation in the Bode plot. So magnitude, then 0 dB, so log omega, that is frequency. So magnitude versus frequency, phase angle versus frequency. So let us say it is a simple example. For different conditions the Bode plots may be different. Okay, different conditions, the body plot may be different depending upon the magnitude of damping frequency, damping ratio, okay, and so on. Okay, so it varies. So this is the point, we can say it is the gain crossover point. This is the point, we can say it is the phase crossover point. So gain is being crossing the 0, here phase is being crossing minus 180. Okay, these are the two important points here. At this point, at this location, we can have this magnitude, at this point we can have this magnitude, so that becomes the phase margin, that becomes the gain margin. So depending upon these two things, we can judge the stability of the system. So for the stability analysis using Bode plot, we require gain crossover frequency and phase crossover frequency. Again we require gain margin and phase margin. So from these four parameters, we can judge the stability of the system. This particular point, at the gain crossover point, this is the phase margin, at phase crossover point, this is the gain margin. So stability criteria, the stability of the control system based on the relation between gain margin and the phase margin is listed below. If both gain margin and phase margin are positive, then the system is stable. So this value should be positive for the stability of the system. If both the margins are equal to 0, if the gain margin equal to 0, phase margin is equal to 0, the system is marginally stable. If both the margins are negative, having value negative, gain margin negative, phase margin negative, in that case the system is unstable. So for the stability criteria, by using the Bode plot, so we require to have four things: gain crossover frequency, phase crossover frequency, then gain margin and phase margin. So we conclude that the second order system, considering the second order system, we are having the transient response, we are having the frequency response, and considering the same second order parameters, say damping frequency, then damping frequency, then damping factor, then resonant frequency, then natural frequency, all these parameters comes into picture when it is being showing the stability analysis. So thank you. If you like this video, then please like it. Also please subscribe my channel by pressing the bell icon button and never miss the updates. So thank you for listening.